This is not our stuff that was here. But we could do it. All right, let's have a look. This was the homework quite some time ago. So if you've done it, you can check whether you got the same answers as I did. If you didn't do it, then do it later. You'll be studying for your exam, I'm sure, so this kind of exercise will come handy. Really, I'm using it as a reminder of what we were doing before the break. And what we were doing was LPs that have nasty things in them. For example, this one is one that has a negative right-hand side. So what you do is multiply the whole constraint by -1. And then, because it turns to be greater than or equal to, you have to use artificial variables and the G objective. And when you solve it, you get okay, the second problem was you have a constraint that has equality in it, so that also needs an artificial variable. You solve the first stage with the G objective, you find a feasible solution, and then in the end you get this optimal solution. And in the third question, we look at problems that have decision variables which don't have to be non-negative. So you know that in the simplex method, everything has to be greater than or equal to 0, otherwise it doesn't work. There is a decision variable which you don't require to be non-negative, then you have to do a trick. And when you do, you get this. So that should be pretty clear. Now, you've got, if you have solved some of these, you can mark yourselves and get 1, 2, or 3 marks, which you can mark here, and that starts the new turn competition. And then also please take one of the here, which brings me to the topic for today. Okay, so the topic for today is called degeneracy. It's not what you think it is. It's a technical term for linear programming. Okay, this LP, can you see anything suspicious about it? Nothing suspicious? One function is what? Multiple of the other. That is suspicious. Yes. That is suspicious. But what does that mean? We don't know yet. Okay, so what we're doing is trying to solve it. Okay, this is the first tableau. You should pivot here. So you should pivot here because it's 2.5 is less than 4. So x2 replaces s1. This row is divided by 2. This row is reduced. You get 3 over 2, 1/2, 0. Is that in the picture? No. It's out when I do this. I can't see it here. Minus 1/2, 1. And the objective row should give you 10, 0, 0, 2, 0. Okay, that's my first pivot step. Can anybody see anything suspicious? Oh. The decision variables are what? Which ones? The objective function is 0? No, it's 10.
Decision variables are
x1 and x2 are the decision variables. That's not suspicious. Oh, there's the 0 there. Is that what you mean? Why is it suspicious? It is suspicious. Well, it's not. Yeah, it is suspicious. Well, it's important more than suspicious. Okay, so there is a 0 here. Where exactly? Well, we have x1 is not in the basis. But its entry in the Z row or objective row is 0. Okay, so that's not something that's wrong or anything like that. But it does indicate one interesting thing. Okay, so first of all, is this an optimal solution? Yes. Why? There are no negative values over here in the objective row. That's quite right. Now, if we pivot on a negative value in the objective row, what happens usually? After the pivot step, the objective increases. Like here, it's increased from 0 to 10. If we pivot on something positive in the objective row, that's what we usually do when we are minimizing, then the objective function typically decreases. It doesn't always decrease, as we'll see next week, but typically it decreases. And on negative, it typically increases. On positive, it typically decreases. What does it do on 0? It should stay the same. Now, if we have an optimal solution already, if we pivot on that and it should stay the same, it tells us that perhaps there could be another optimal solution. So let's try to do another pivot step where we put x1 into the basis. The x1 enters the basis. The ratio test is 5 and 3. So 3 is less than 5. So S2 is leaving the basis. The basis is x2, x1. The pivot row is just multiplied by 2, so we should get 3, 1, 0, minus 1, 2. And when we row reduce, we get 1, 0, 1, 1 minus 1 is the x2 row, and 10, 0, 0, 2, and 0. In fact, we have to get the same objective row because there's already a 0. Well, we need 0, so there's no row reduction going on. And is this an optimal solution? So we can see there are at least 2 optimal solutions. Which is nice. Well, which could be useful sometimes. Sometimes it's not. Okay, so what have we done? We have found 2 different optimal solutions. So the first one is x1 is 0 and x2 is 5/2, and the objective is 10. And in the second one, what did we have? X1 is 3, x2 is 1, and z is 10. Okay, this is called degeneracy. So when a linear program has more than one optimal solution, it's called degeneracy. Anything wrong? Okay. So, football. Is there another optimal solution other than these 2? X1 is 1 and x2 is 2. Is there one like that? Presumably. Okay, so guess. X1 is 1, x2 is 2. Okay, what's the objective? Well, the objective is 2x1 plus 4x2, which is indeed 10. So that's promising. Does it satisfy all the constraints? Well, x1 plus 2x2 has to be less than or equal. Oops. Well, that's not a good idea. X1 plus 2x2 is 5, so that's less than or equal to 5. And x1 plus x2 is 3, so that's less than or equal to 4. So yes, there is another optimal solution. Did you just guess it? No? How did you find it? It has to be 10, otherwise it's not optimal.
Yeah.
Can't be more than 10 because 10 is optimal. Well, at least if we trust the simplest method. But it can't. But if it's less than 10, then it's not optimal. Okay. So yes, there is an okay. So who thinks there are 3 optimal solutions? So who thinks there are 4 optimal solutions? Okay, 5. 28. More than that? How many? Yes. There are infinitely many. But why? Okay, so why? How do we find them? What? No. It's got to do with the following thing. What? Definition. Okay. So we have 2 vectors. One of them is called x, and let's say it has coordinates x1 and x2, and the other is x dash, x1 dash, x2. What we find is a convex combination of these 2 points, vectors, if you like, is any point vector can be written as alpha times x1, x2 plus 1 minus alpha times x1 dash, x2 dash. For some scalar or real number, which is between 0 and 1. That's just a definition. What does this definition mean? Okay, it's a bit of a non-transparent definition when you first see it, and I admit when I first saw it, I was completely confused. So don't worry if you're completely confused. Okay. Algebraically, what it means is does anybody have any specific questions about this? Okay. So once again, what you get is one vector that has 3 entries, x1 and x2, it's a 2-dimensional vector, and another one, and then you say that the convex combination of these vectors is you take any number alpha between 0 and 1, real number, you multiply first vector by alpha and the second one by 1 minus alpha. Okay? That's the definition in algebra. You've been doing things like this in your linear algebra, multiplying vectors by numbers. Okay. This is that. This is that. So for example, so if x is 0 x1 is 0 and x2 is 5 over 2. That was our first optimal solution. And x dash is 3 and 1. And completely randomly, I pick alpha to be something between 0 and 1. So let's say 2/3. Okay. So what do we get? 2/3 of 0 and 5 over 2 plus 1 minus 2/3, so that's 1/3 of 3 and 1. So this is 0 and 5 over 3, multiplying that, plus 1 and 1/3. So when we add them, component-wise, we get 1 and 6/3, so that's 2. So x1 in the first coordinate of this vector is 1 and the second is 2. Okay, so that looks suspiciously like the guess. But that was just random because I selected 2/3 completely. It looks like magic, but no. Now we don't know where this is going. Never mind. We'll soon see where this is going. Okay, so what does this convex combination, in fact, what does it mean? So have you heard the word convex before? In what context? Convex angles. Oh. Yes. So diversion. Okay. Convex polygon. Is that a thing? Yeah. What does that mean, actually? No. Okay, so there's a difference between these two polygons. No. There wouldn't be a difference if I continue. Can you see it? Okay, so this one has an angle which is larger than 180 degrees. Okay, this one has one particular thing, which is you can find 2 points in the polygon. And if you look at the line segment between them, it doesn't lie in the polygon. It's not inside the whole of it. Whereas in this one, no matter what 2 points you pick, the whole line segment will be inside the polygon. Okay? So that's the distinction between convex things and non-convex things. So this thing is non-convex. And this is convex because of that. So while we're diverting, when you look at, in fact, the meaning of the convex combination is when you get 2 points. What point do we have? 0 and 5 over 2. So this is x1. 0. 5 over 2. So this is 1 point. Um, the other point was 3 and 1. 3. This is 3, 1. This one here is 0, 5, 2. Where's 1, 3? 1, not 1, 3. 1, 2. So 1, 2 is here. And it's not a coincidence that 1, 2 lies on the line segment. Because in fact, convex combinations of 2 points form the line segment. Yeah, that's what happened. If you pick your alpha to be 1, you get 0, 5 over 2. You pick your alpha to be 0, you get 3, 1. Pick it to be 2/3, you're closer to the first point. You get the center of the line segment when your alpha is 1/2, and as your alpha gets close to 0, you get close to this point. So that's how it works. Where this is heading is, in fact, that is this was an optimal solution, and this was an optimal solution. So anything on the line segment is going to be an optimal. So any convex combination of 2 optimal solutions again. That's a statement. Where's the proof? Proof is proof. Okay. I'll call it a lemma. Find 2 optimal solutions. Now, X star and X double star of an LP. Then any convex combination is also an optimal solution. Okay, I'll give you the proof too. I'll give a couple of diversions before we get there. First of all, I want to, okay. First of all, there is nothing magical about the number 2. Why is there a 2? Okay, there are 2 2s in that stupid definition, which is completely ridiculous. First of all, both vectors only have 2 coordinates. Of course, you know that vectors have, I hope you know, I don't know what's the. Let me show you vectors that have 17 coordinates. Oh. The vectors have 3 coordinates. N. Yeah, so n can be 17. That's cool. Okay, so they can have n coordinates, not just 2. And there can be more than 2 vectors as well. Okay, so we need to find a better definition. Diversion. This is a complete diversion. So, because I want to learn something as well. So, for example, so we had x is x1, x2. Is this what you're used to? Like the first entry is x1 and the second entry. Yeah. So what happens if you have n vectors? What do you call them? I don't want to introduce a different notation to use. No, not base. No. I mean, like, can you have vectors that are called x1, x2? Yeah. What would you call the first entry of the second vector? Okay, something like x2, 1. Okay, so that's a definition. So let's take x's. x1, 2, xn, and vectors, and there are d-dimensional. So each of them has d entries. Convex combination, make it nasty. Unreadable now. Sorry. Of x1 to xn is any point or vector. Okay, what do we need to do? What were we doing before is we took some scalar alpha and 1 minus alpha. We multiplied one of the vectors by alpha and the other by 1 minus alpha. Okay. And they both have to be between 0 and 1. Obviously, if alpha is between 0 and 1, then 1 minus alpha is also between 0. That's the key. Okay. So what we get here is we multiply multiply each of them by a scalar and add them all together, and that's a convex combination. But it's not but like this, it's not a convex combination. So, not finished yet. So what do you call this? Yeah, you call this a linear combination. But the convex combination is a special case of a linear combination. And there are some extra conditions. The first condition is that all these alphas have to be between 0 and 1. For each I, alpha I is between 0 and 1. And the second condition is that when you add them all together, you get 1. Okay? That's the best definition. I'll call this A and B. So as you just said, without these conditions, if you don't have these conditions, it's called a linear combination. And without A, if you have B but you don't have A, it's called an affine combination. So you won't need this. You don't have to know this, but it's always good to know something you don't have to know. Then you can impress people. You know everything that we want to know, that we want you to know on the exam, then you don't impress us. You just, we're expecting you to know. But if you know something extra, then that's impressive. So in this geometry picture that we have, we have those 2 points that we have. This one. What are all the linear combinations of them? Basic linear algebra. This is what's the rest? Okay. What are all the linear combinations of these 2 points? 0, 5 over 2 and 3, 1. Plane? No, the plane. Okay, sorry, I didn't hear you and I thought you were right. You're always right. Must be the first time. Okay. In fact, yeah, so if you do, you can do anything. So if you're allowed to your coefficients to be anything, you can get any point in the whole plane. If you insist that they all add to 1, then you get the line. So the affine combinations are all the points on that straight line. And if you moreover insist that all the alphas be between 0 and 1, then you're restricting yourself to the one thing. Okay. geometry. And one more thing before the break. You can do a corollary. Of the lemma. Do you know what a corollary is? I told you half a year ago or so. It's like a theorem, but it's an easy theorem which immediately follows from something you know already, like from the lemma. Okay, so first corollary of the lemma is that if you get n different optimal solutions, of NLP, then any convex combination of them, so is also optimal. Did Killian teach you proof by induction? Saeed did. Even better. Okay, so this is corollary 1. Corollary 2 is that if a linear program has what do I want to say? More than one? So if a linear program has more than one optimal solution, then it has infinitely many. Well, that's absolutely obvious because you have two distinct ones, then any convex combination is also optimal, and there are obviously infinitely many convex combinations because you can pick your alpha to be any number between 0 and 1. So that's probably enough for now. So let's take a 10-minute break now, and then after the break, we'll discuss this and prove the lemma. Is anybody going to stay? If you study biology here, you get to go to Africa to take pictures of elephants. I think mathematics should introduce something like that. We do a trip to Australia to photograph equations. Yeah. Um, yeah. Let's get in there. Okay, let's do a couple of more. So, firstly, the first example that we have, the feasible region looks like this. We look at it, and all the optimal solutions are really on this line segment. So, the first one we found was this one, I think. The second one we found was this one, and then anything on this line is an optimal solution. They're all of them are convex combinations. Now, one thing that I was asked by in the break is why there is a difference between, what is the difference between dilemma and the corollary. So the first lemma says that if you have two optimal solutions, then any convex combination of the two optimal solutions is also optimal. Now the corollary says if you have any number of optimal solutions, then any convex combination of these optimal solutions is also optimal. So maybe I should have said, so the first corollary has a geometric interpretation. So for example, if n is 3, it's one of the, okay, so because these things, well, for linear programming, these things only get interesting if you have more than two decision variables, because you either have, okay, I'll say that later. But you have three, then, for example, what can happen is that you have three different solutions like this. And then, so x1 star, x2 star. Okay. So you know that all the, well, we already know that all the convex combinations of any two of them form line segments like this. And then when you add a third point and take all the convex combinations, that triangle. Okay, so if you have these three, it could be basically the solutions, and the whole triangle is, that's the convex combination. The way it's actually it works is you take any convex combination of x1 and x2, and then this line segment is then all convex combinations. That's
That's the geometry. I think the geometry is always quite nice because you get to see pictures and that's the next step. Find the register. Okay, can you sign again? Like, make a no, make a star if you're still here, because this is the phenomenon that I think 80% of the class leaves. Okay, so this is how you go about it, because you know that well, these you can really split it into two. So when you have a convex combination of all the three x's, it's going to be something like alpha 1 star, alpha 2 star, okay, plus 3. So in fact, what you do is you could see this as a convex combination of does it work? So yeah, I don't want to go into all of that, but you know, you can see every convex combination of 3 points you can do step by step from the pairs, and that's how you see the follows from that. So first you look at 2 points, and then you find a convex combination, and then you look at the third point and you do a convex combination, and like this you get the whole down. Or you could have 4 points, 5 points. If the 4 points lie in the plane, then you get a quadrangle. And if they don't, then you get a simplex like there are very nice geometric things going on. To answer your question. Good. There are some cases. So, for example, the case we have. So let's say it and think again. You could have a bounded feasible region. What's that mean? Well, that means that it doesn't go to infinity anymore. For example, this could be the feasible region. Okay? And then either you have one optimal solution, and then unnecessarily there has to be a basic feasible solution, or you have infinitely many, and then they form convex combinations of 2 optimal basic feasible solutions. So that would be the case when this whole line is optimal. Okay? So that's exactly the example that we saw in the first one. But also you could have an LP that has an unbounded feasible region. The feasible region could look something like this. So this whole, this green area is in here, and in here the unbounded, so going to infinity. Does it look green? Green. So that green area would be, in that case, it could happen that all these solutions could be optimal. So you have infinitely many optimal solutions, but only one of them is a basic feasible solution. So only one of them is this corner here. Okay. That could also happen. So if you have an unbounded feasible region, then you can either have one optimal solution, which is a basic feasible solution, or you could have infinitely many, and in this case, you could have, it could be a line segment right here. Okay, so this is, one option is that you get a line segment of optimal solution, and another option is that you get a half line of optimal. So in this case, it could be either one basic feasible solution, so that's the fifth case, or two basic feasible solutions, which is the other case. But in this case, if you have an unbounded feasible region, then you can also have no optimal solution. And we did that before. So you would have no optimal solutions if you can make the objective arbitrarily large. That's yeah, so summary is it's a bit like this. Get infinitely many complex combinations of two optimal solutions, and you find the two basic feasible solutions because you pivot on something where there's a zero in the objective. So on a non-basic variable in the optimal solution. And the other case, well, okay, if you have this case, then what happens is you find the optimal solution, then there's a zero in the objective row of a non-basic variable. So you want to pivot, but you can't pivot because all the other elements in that column are either 0 or negative. You couldn't pivot to get the other basic feasible solution. In that case, you get the whole solutions. Anything else that I wanted to say? Yes, this is the case of two decision variables. And of course, if you have more than two decision variables, then there are various funny cases. So you could have a triangle of optimal solutions, but you can't with two variables. Unless unless the objective function is something trivial. Or other things can happen. So that's how to hard to visualize, because if you have a four-dimensional set of optimal solutions, then and hard to draw in a 20-dimensional space. Any questions about this? Okay, proof of lemma. Off the record, it could be useful to know this proof if you're planning to take the exam. I can say that because you've remained here with my faithful team. So yeah, please do remove it from the recording. Nobody watches the recording. Proof of lemma, useful. Okay, so first of all, let's go back and have a look at what's the lemma, where it says. Yeah, what it says is if you have two optimal solutions, different optimal solutions, well, maybe they're not different and all convex combinations are the same point, so that's not. So if you have two different optimal solutions that are in the program, then any convex combination of these two solutions goes what? So there are two things that we have to prove. The first thing is that it's a feasible solution at all. And the second thing is we have to prove that it's optimal. So it has as good value of the objective as the optimal solution. So we need feasibility and optimal. Okay. So I'll call this convex combinations Y, to have a name, and it's going to be alpha times x star plus 1 minus alpha double star. Alpha is a real number. 0. So this is the definition of a convex. We're trying to prove that Y satisfies all the constraints of the linear program. Now, what is a constraint of a linear program? So a constraint is a linear inequality. So it looks something like A1 x1 plus A2 x plus A d x is less than or equal to d, greater than or equal to d. Okay, now we know that both the x star and x double star satisfy this. So what we want is A1, Y1 plus A2, Y2 plus A and Yn. So now Y1, Y2, Y3, those are the components of the vector Y. So this comes from multiplying things by scalars, vectors by scalars. You're doing it entry by entry, and then you're adding them entry by entry as well. So here you get that Y1 is alpha times x star Y1 plus 1 minus alpha times x double star 1. This thing, when you're calculating it, first coordinate and second coordinate and third coordinate, anti-vector. But in fact, 1 is another thing, so I don't need 1 pi. In every coordinate, it's going to be like this. And therefore, so what happens when you do A1, Y1 plus A2, Y2 plus AD and B is that you get, maybe I should use the sum notation. Okay, so yes. Are you very good with the sum notation? It's easy to use. Okay. So this is I goes from 1 to 3. So now we know that yi is that thing over here. Okay. So you can do the sum from 1 to d of those things over there. Alpha times I've lost something. Hang on. So now you can reshuffle the sums, expand the bracket, and put things to different places. And what you get is I goes from 1 to b, alpha x star plus another sum now goes 1 to b, a 1 minus alpha x star. You agree? Yeah. That's just expanding the bracket of the AI and then making two different sums. Okay? And in those two different sums, I can take alpha and 1 minus alpha because it's constant within the sum, so I can take it out, and I get alpha times this plus 1 minus alpha times 1 to b star. You still with me? That's just a manipulation. And now, So now, what's going on here? Okay, so this is the left-hand side of the constraint when you plug in x star. And this sum is the left-hand side of the constraint when you plug in x2 star. Okay? Now, because these start things, they're optimal solutions. So in particular, they have to satisfy the constraint. So this sum is no more than b. And this sum is no more than b. And we multiply each of them by a non-negative number, so that remains less than or equal to b as well. So this is less than or equal to alpha times b plus 1 minus alpha times b, because these two things are feasible solutions. What's this? Yeah, this is b. So that's it for feasibility. So let's have another look. We have a constraint looks like this. We want to see whether if for x, we substitute y, whether it's satisfied. Okay? So when you substitute y, you get this, and you calculate, and you I know that this is less than or equal to b, so it is actually correct. And any constraint of the linear program is like this. But in fact, you have non-negativity. Non-negativity is also like this because b is 0. A1 is -1, and the rest of it is so any constraint is element. So indeed, y satisfies all constraints. Make any sense? The second thing is my optimum. The objective function is Cx for some vector C, okay? So Cx in fact is the sum of Ci, Xi, in the product, that scalar product of C and X. So that's the objective function of the vector. I don't know what it is, but it doesn't matter what it is exactly. It is linear like that. Now, what is this objective for y? Well, comes from y is. So I to get the sum again, C on y, which is the sum of C on times. What is yi? Well, it's alpha times x plus 1 minus alpha times x 2 star. Okay. So again, if we reshuffle the sums and do all kinds of some things, what you get is that this is alpha times, in the same way as before, C r plus 1 minus alpha times r. In other words, this is can you say anything about these two numbers? Three times the inner product of C of x star and the inner product. For example, which one is larger? Which one is smaller? Rather than the same. Yeah, wait. Gotcha. Okay, I repeat my question. The value of this and the value of this product, are they the same or are they not the same? And if they're the same, why? Exactly. It's smart. Yeah, these two things are the same because they're both the optimal objective. So what we're assuming is that this x star is an optimal solution and this x double star is an optimal solution. So if you put it into the objective function, if you put that one into the objective function, you have to get the same number. If you don't, then one of them is not optimal. So they have to give you the same answer. So that means that I don't have to use the two of them. I can just use one. So this is the same as this. So that means that if you put y into the objective function, you get the exact same value of the objective function as you do for x star or x double star, and that's the reason why y is optimal. So look at how what's that an easy one. It's not fun going on. Okay, so there are, it really is very straightforward because you can just show that it's y defined somehow. Sorry, the convex combination is it's both feasible and optimal. So that it's feasible, you plug it into a constraint, and you see that's satisfied because it was satisfied by the x's. And to show that it's optimal, you plug it into the objective function. See that you get the same value as you did for the x's. For optimal, you get the same value. And the rest is just there's no deep idea there. Any questions? There's a second form of degeneracy in linear programming, which is when don't really spend any time on it. No. Yeah. So what we're used to is constraints look like this. And then you might have another one, and here you have a few degrees. So it can happen that you get another constraint that goes through the same intersection point. You might even have another constraint that goes through the same intersection point. So what we were used to was that you get one basis, another basis, and one basis here, and that was the normal situation. But if you have several constraints going through the same point, then there will be many different bases in this point, and that can somewhat get nasty, but we'll only do that next week. For this week, that's unless you have issues. Is this Friday the deadline for the coursework for the first 4? How many have you submitted? All? No, it's good. Okay, well, that's it then. Have a good evening. See you around.